So hello everyone, and thank you all for joining in this session. Today I'm going to share with you how we at Riskified took a concept from an entirely scientific domain and used it to beat our own production models. So as our title suggests, we will talk about how to choose the right data. But before I'm giving away all the answers here, I would like to refer this question to you. So what kind of samples would you want to train your models with? What will happen next is that I'll show you a chart with different examples, and you will need to vote on your preferences. Just before we move on, we will see a result of a classification model, but we won't look at it as a final product, but rather as a process. Okay, so classification model results, in our case, boosting tree classification model. Each line here represents a single sample from our training set. Green lines refer to class equals 0 or legitimate orders, and red lines refer to class equals 1 or fraudulent orders. The y-axis is the outputs of the model, the score, and the x-axis is the trees of our model. So if we are looking at a single line here, we can see for a single sample, what is the score that it got along the trees of our model. Overall, we can say that our model is doing quite a good job, right? Good orders get low scores and bad orders get high scores. Or for the samples that we see here, we can say that our model pretty much understands what needs to be done, and we can call these easy to learn. Let's look at a different example. So now we see a red sample in our green area, or a bad order that is getting a low score. Not only does the model misunderstood this one, but he's pretty confident about its decision. We can see that the slope here is quite steep. So for this type of samples, we will call hard to learn. And now for the third and final example here, this is quite different. We see two green lines, two good orders, that the model starts by giving them a high score and then changes his mind. So if we are looking at the final trees here, the final model score is low or lower than 0.5. But from checking the inner trees, we can tell that this was quite challenging to our model. Now, my question to you, out of the three types of samples that we see here, easy to learn, ambiguous, and hard to learn, what type of samples you think are best to train your models with? And I think I can only see like the host, so please think about what you would choose and keep in mind your answer, and we will move on. Okay, so today we will get familiar with a sampling method called data maps, and I will show you how you can use it to identify samples that will help you best train your models. A little bit about myself. So my name is Racheli, and I'm a data scientist at Riskified. I'm doing a lot of research and work around different sampling methods, and also I really love to work with visualization and really believe in good visualization. And you'll probably get to see it through this session. Cool. So let me start by stating the obvious. We can't and we probably don't really want to use all the data that we have in hand. In commercial companies, we usually deal with huge data amounts. Not everything is labeled and not everything is of the highest quality. And many times in our day-to-day, we see patterns that we don't really want to show and train our models with. So although this is quite a consensus that in the machine learning world, good data is essential, let's be honest with ourselves. Many times we don't really know to tell what does good data even means. So we will want to have some magic trick to tell us what are the good samples in order for us to use them. In our session, we will take the spot out of the models and put it on the data. We will have two parts for this session. First part, we will get to know the data maps approach taken from a paper called Dataset Cartography, Mapping and Diagnosing Datasets with Training Dynamics, written by Allen Institute of AI together with the Hebrew U. And in the second part, we will face reality, and I will share the work we have done at Riskified to take these concepts and leverage it into a structured sampling methodology that really suits our needs and overcome our challenges. Cool. So before we dive in, just like a quick intro about Riskified, who we are and what we do. Riskified is a company providing risk and fraud detection solutions in the world of e-commerce. Our solutions are machine learning based, and basically we are integrated within our merchant sites, and we analyze for them their orders to decide whether these are good orders or fraudulent orders. How does fraud classification data looks like? At this point, it's important to stop and say that the vast majority of orders in the e-commerce world are actually legit and get approved. Number varies between different industries, but we are talking about like 1% fraud. We can see here an illustration of our data, legit orders in green and fraudulent orders in red, and some threshold for us to decide whether we suspect an order to be fraudulent and decide to stop it. Let's take it to terms that we like to use. So on the approved side, we have a lot of true negatives. We call them good approvals, but we also have false negatives. We have an indication for our false negatives because people file something that is called a chargeback to get their money back. What's going on the decline side? So here we have true positives. We call them good declines or fraudulent declines, but we also have false positives, wrong declines. The problem is that because we have decided to stop these orders, we don't really have a good indication on what the true label of this order really is. So we have here two main challenges. One is that our data is highly imbalanced. And the second challenge is that our minority class is basically masked. So we will put these challenges aside for only a few slides and start to discuss our sampling methodology. We have here 3 steps for sampling methodology. First, we start off with an initial model we already have in hand. Based on this model, we will want to assign to each sample in our training set a value that tells us how good or how important this sample is to our training process. We will call these values training dynamics. In the final step, we will take our training dynamics and create a data map visualization out of it and use it for our sampling. Okay. Remember the chart that we started off with? This is exactly what training dynamics is all about. The basic idea of training dynamics is that we want to measure the score change of individual samples along the training process. I would say that again. We want to measure the score change on individual samples along the training process. Actually, this is exactly what we see in this chart, right? But as much as I personally love this chart, and I think we can further discuss it and go into it, but we need something that we can work with, right? We need something that we can actually sample from. So here we have our training dynamics-based metrics, 3 metrics that we will calculate per each and every sample in our training set. First metric is confidence or the mean score. Again, we are calculating the mean score per each and every sample. Second metric is called variability or the squared standard deviation of this mean score. And for the third metric, we call it correctness. And here we involve our decision boundary and basically ask per each sample, how many times was I above or below a certain threshold, or how many times was I correct or mistaken? So we moved from a situation that each sample is represented by a vector of scores to a 3D representation per each sample, confidence, variability, and correctness. Now, let's visualize this. What we see here is exactly our data maps visualization. Every point here is a single sample from our training set. The x-axis is the variability, the y-axis is the confidence, and the color dimension is our correctness. We will better understand what's going on by looking at the different type of samples that we see here, but we can already tell that these three metrics are highly correlated with each other. Okay, so our first area of interest is the easy to learn. This is where all the easy to learn samples from before are being mapped to. We can see that confidence is high and variability is low, meaning the model is pretty confident about its decision and doesn't change his mind through the training process. Second area is the hard to learn. So here too, we see low variability, but confidence is low too. What does it mean to have confidence close to zero? It basically means that the model is pretty confident about its decision, but he's entirely mistaken. According to the article, what we will see in this area is mainly noise, bad labeling, or samples that are too complex, edge cases that the model was not able to learn and will probably won't be able to learn in the future. Our third area of interest is, of course, the ambiguous samples. Here we see samples with medium confidence, but more importantly, with high variability. And according to our article, this is the area where we will see the most important samples to our training process. These samples are not too obvious, but not too complex for the model to understand. Here we will see the interesting pattern in the interesting connections between different features. And this data will help us to gain the best model and the best generalized model. So going back to the question we started off with, what type of samples will we want to train our models with? The short answer here is that we will want to use the ambiguous data. And the bit longer answer, or our recipe for success, is as follows. We will take all the ambiguous data because ambiguous are the most interesting and important features for the models to learn from. We will drop the hard to learn because hard to learn is correlated with noise. And we will add to this recipe some easy to learn to help our model converge. Sounds easy, right? Sounds pretty straightforward. But let me remind you of our challenges in the fraud detection world. So we said that our data is imbalanced. We also mentioned that we do not have the true label for our declined population. And I'm adding here a new challenge. So before I told you that we have an indication for our false negatives because users file something that is called a chargeback. But the truth is that people file chargebacks from different reasons. Some are legit and some are not so much. So we can already understand that we can just like naively eliminate hard to learn, take all ambiguous, add some easy to learn, and things will work out fine. And our sampling mechanism will probably get more complex than that. Cool. So just want to show you a quick reminder of our original data map taken from the article. Everything is nice and tidy and super symmetric. We have done the work on our side to represent our data in the same way. And I'll just mention here and give credit to Elio Cohen TensorFlow implementation available on his personal repo for this entire concept. So we've done the work on our side and created a data map for our fraud detection models. And this is what we've got. This is a data map for a single fraud detection model. A single fraud detection model is a model aims to detect fraud for a specific industry or even in a specific merchant. Let's understand the differences by looking at the different type of samples that we have here. So first, we have a really high density on the easy to learn area. Many obvious cases, obvious good or obvious fraud. Second difference, much less ambiguous than what we've expected or hoped to see in our data. And the third and last difference here is we see a new area that we didn't see before. We called it no decision. You can see that the confidence, like we have medium confidence and low variability. And you can imagine it as something like the model is not making any decision given a score of 0.5, but being consistent with that no decision along the way. So quite different than what we have expected, right? But don't worry, we didn't give up at this point. And actually, once we've started to use this data map with different filters and for different labels in our data, it made a lot of sense to us and really helped us to understand how we want to use this concept to sample from our data. So let's see some examples. First example is for chargebacks. So here we see the same data map, only filtered for the chargebacks population. We see two areas of high density. One is the easy to learn we saw earlier, but the second area is the hard to learn. Recall that the article suggested that hard to learn is correlated with noise. We have decided to test that and sent a sample from this population for manual tagging. What we've come out to realize is that we actually have a really good automated mechanism in hand to detect what we call non-fraud chargebacks that we do not want to show to our fraud detection model. So for the chargeback population, we don't have too much chargebacks. We can't like eliminate them and play with them too much. So for the chargeback population, what we've decided to do is just to clean up the hard to learn chargebacks. Let's see another example. So here we are looking at the same data map, only this time filtered for good approvals. Good approvals, we have a lot. We can play with and work with them and do whatever we want with them. What you can see on the data map is that we have even more extreme high density around the easy to learn area. If we are looking at the most obvious cases, cases where confidence is close to 1 and variability is close to 0, you have a really even more extreme density in that area. So we understand that just like randomly sampling from this population won't do, and it will just give us like the most basic cases, and this is not what we want to do. For this population, we've used a really cool trick called inverse sampling. First, we created the density function on the data map space, on the confidence variability space, and then we've used the inverse function to create our sample. So I won't go into details, but basically we will manage to take the original distribution and flatten it. So our sample will be relatively uniform around that data map space. Okay, so we saw an example for chargebacks and we saw an example for good approval sampling. I won't show you any more examples, but I do want to zoom out to understand the mechanism that we've got here. So we said that we are starting off with an initial model. In our case, we are using the production model, but you can also use like an initial iteration of your model. Using that model, we are calculating the training dynamics per each and every sample in our training set, confidence, variability, and correctness. In the final step, we are using the training dynamics to create our data map and sample based on this data map. In the Riskified world, a little bit different per each and every label. Great. So just want to wrap up things before we end. We have seen the concept of training dynamics, and so it's a really cool tool and really can help us to understand what our model is seeing and how our model is performing learning. And we saw the data maps concept, data maps visualization, and data maps based sampling, and understood how it can help us to best choose the data that we show to our model, and by that get a better performances. That would be all. So here are like relevant sources to the concepts that we talked about. And that is it. Thank you for your time.